In this video, I'm going to build a neural network from scratch. What I mean by that is we're not going to use any deep learning libraries like Tensorflow or Keras. We'll just use Python and numpy to build the neural network. We'll build a neural network that solves the XOR problem. XOR is a logic function that's almost identical to the OR function. Here's the truth table for the OR function. 0 or 0 outputs a 0, 0 or 1 outputs a 1, 1 or 0 outputs a 1, and 1 or 1 outputs a 1. The XOR function has the same truth table as the OR function, except this last row is different. When both x1 and x2 equal 1, this yields a 0 in the XOR function instead of a 1. And all these other entries here are the same in the XOR function. This XOR truth table is a tricky thing for the neural network to represent. In fact, Minsky and Papert in the late 1960s showed that neural networks at the time, which were called perceptrons, couldn't solve this problem, and this killed neural network research for years. So we'll build a neural network that solves this problem, and the neural network will have an input layer where x1 and x2 are the values for them are input into the input layer. We'll have one hidden layer which has just 2 nodes and an output layer which contains a single node. 3 steps are taken to train a neural network. The first step involves putting a training data example through the network. So passing one or more data examples through the neural network, and that's called forward propagation. This leads to the neural network outputting or predicting a value between 0 and 1 at the output node A, shown here in the figure. The second step of training involves using a loss or error function to determine whether the output or the prediction of the neural network is a good one. The value the neural network outputs is compared with a target value. And the target value is, the true value that the neural network should have output for a given training example. The loss function gives a number, which is the amount of error that the neural network's guess has. The third step of training a neural network involves assigning blame to the nodes of the network for the error that occurred when the neural network made a prediction. So this third step, this training step, involves changing the weights of the network. So W5, W6, W1, 2, 3, 4, and their bias, all the bias values. Training involves changing those weights up or down, moving them up or down, so that the next time the neural network makes a better prediction. This third step, where the weights and biases of the network are adjusted, is called back propagation. And these 3 steps of training take place in a loop. So a data example is fed through the network during forward propagation. Forward propagation outputs a prediction or a guess for that example, and a loss function evaluates how good or bad the prediction was. Backpropagation then happens, and it goes backwards through the network to adjust the weights and the biases so that the next time the network sees the same or a similar data example, its prediction or guess will be better than it was this time. And then we go back to the start of the loop again, and another data example is fed through the network, the loss is computed, and backpropagation happens. This training loop is executed thousands or tens of thousands and hundreds of thousands of times, and it's in this loop that the neural network is trained and learns how to make better predictions. The equations on the right here are the equations for doing forward propagation in the neural network. And as a reminder, here is the truth table in purple for the XOR function. And we're going to see what value the neural network predicts when x1 is 0 and x2 is 0. So this first row of the truth table. The correct answer would be 0, but the neural network hasn't been trained yet, so it's probably not going to output that correct answer of 0. We assign random values to the weights and bias terms before training happens, and so the neural network is very likely at the beginning of training to output really bad predictions. But those predictions will improve as training progresses because we'll be adjusting the weights and biases. The values of x1 and x2 are fed into the neural network here in the input layer, and then the value of h1 is computed. As you can see here, it's a weighted sum of x1 and x2, and we have a bias term. And the sigmoid function is then applied to that weighted sum. Sigmoid function will output a value between 0 and 1. Similarly, a value of h2 is also computed. It's a different weighted sum because it has different weights here. It's a different weighted sum of x1 and x2 and has a different bias term, and the sigmoid function is also applied to it. So h2, like h1, will output a value between 0 and 1. And then a weighted sum of the values of h1 and h2 are computed at the output layer here, and the node A has its own weights, W5 and W6 here, and its own bias term. And again, sigmoid is applied, so it outputs, let's say, in our example, a value of 0.99, which is almost the worst answer it could have output because the correct answer is 0, and it output basically a value of 1. So it's almost as far away from the correct answer as it could be. We need to get some sense of how accurate our neural network is. And so we have an error function, or it's also called a loss function, which will tell us how much our prediction that the neural network has predicted, how much that prediction differs from the correct answer it should be outputting. So this is what the cross-entropy loss function looks like. And so in our case, the correct answer was y equals 0, but our neural network output a value of 0.99 here. So when we plug in those values, we see that we get an error or a loss of 2. We want the neural network to make predictions such that the loss or error function is really low, so that it's as close to 0 as possible. And as the neural network trains, it's going to get better and better at making predictions. And so the loss function is going to continually decrease as training progresses. Let's take a look at another example. Let's say the correct answer to output is y equals 0, and the neural network outputs a value really close to 0. If we plug in those values, we can see that the loss function or the error function here is really close to 0, which is good, because the neural network made a good prediction in this case. So in the last few slides, I've shown how the cross-entropy loss function is working as it should. When the neural network makes lousy predictions, the loss is some value like 2, and when the neural network makes good predictions, then the loss function equals 0 or values really close to 0. We've seen in this video how to implement forward propagation and what the loss function will be. In the next video, we'll take a look at how to implement back propagation.